All right, here's the theory section for chapter 2, sections 1 through 5, where we're going to define stress. All right. I said I would try, or I will, at the beginning of every section, list our course learning objectives for this little slide packet. And the course learning objectives are that we would apply the definitions of stress, normal stress, and shear stress for solving any variable, so we can rearrange those equations, and then use those equations to derive things later. So we won't do the deriving later, but we'll use those equations as presented, and we will solve for stress in various objects. The equations from the study guide that we need to be aware of are right at the top, equations 2.2 and 2.4, which are the definitions of this average stress. Sigma average, that's the normal stress, is equal to F over A, F being the force, A is area, and the shear stress, tau, shear stress average, is equal to V, the shear force, divided by A, the area that is being sheared. So the first kind of stress we're going to talk about is tensile stress. That's where we take an object and a structure like this is called a dog bone. And we are going to pull on that dog bone to get it to have a tension that's showing up across that section AA. Now, this would actually go back into the page and we would have, and we'll see something like that on I want to say on the next slide, but it's 2 slides from now. That's going to create a tensile stress that shows up on that plane that if it's large enough, if the tensile stress is large enough, it will cause the dog bone to fail. Why is that important? Well, that's what we're studying. It's important because we are studying that failure point. So this allows us, all of this information gets us to a definition of stress, which is what we saw of tensile stress, which is what we saw, second slide, that my normal stress is equal to force divided by area. Now, we've got to be a little careful. I'm using capital A. That is not the same as this A. This is, if you remember your Engineering 181, that's how you label a section view. All right, we're talking about this cross-sectional area. I'm going to go in red. That cross-sectional area of the 3D shape, yeah, that's the area. The force is, well, we're identifying that force there, but that's the reaction force to the force that we applied, P. But that gives us our definition of tensile stress. Sigma is equal to F over A. Now, one of the things also that's going on is this is an average. We did not look at locally what's going on like we're going to do on the next slide. On this slide, you can see, yeah, maybe we don't want to think about that. Maybe we don't want to think about that as the total force and the total area, and then come up with an average stress, because that's not the way actually things break. They break locally, and then that shifts the force distribution. So we kind of need to be a little bit careful. Now, I really don't want to do this, and as you get to know me better, you'll realize how little I really want to do this. But we might want to take the definition that we had on the last slide, which was sigma is equal to F over A. And if we look at it in light of this slide, we may want to change it that this is the integral over area of the stress, which is a function of the area, dA is equal to F. This definition is going to help us later. Now, if the stress is constant, then this just becomes rearranged, and right, it would just be sigma A is equal to F, and then we get the equation that we had previously. But if we have a distribution, well, we have to worry about that. There are going to be a lot of times in this class, unfortunately, that we're going to have distributions, and the calculus is going to show up. Sorry about that. Sorry about that. Next slide. Next kind of force, next kind of stress. This is shear stress. This is shear stress. Shear stress shows up when two objects are trying to slide past each other. All right, and so this shows up in two different joints here. If you look at this from the top, if you look at this structure from the top, they ran a bolt through here and a pin through there, and that's good. And then we start pulling these things apart in the lower view here. Now, that's going to cause this upper portion of the bolt here to want to go that way. But it's going to cause this lower portion of the, I got to get a better color, this lower portion of the bolt to want to go that way. And there's this region in the middle where that surface is in shear. That surface is trying to be, the top is going one way and the bottom is going the other way, and there's that place in the middle where they are in shear. It's a little bit harder to think about, and I hope some of the demonstrations in class with the deck of cards or with the insulation will help. But this leads to then a new equation and some new principles. This is going to lead us to the equation shear. The shear stress is equal to the shear force divided by the area, and now it's that area in shear. Shear stress, tau, is equal to the shear force divided by the area. All right? I want to encourage you to remember these, not based on the symbols, but based on the language, because that, if we start using, if you start saying tau is equal to V over A, you'll get lost in some of the details. And when you get to some of the homework, what you'll battle is a situation where I just had to solve, we just solved a problem where I used tau and T for thickness. And, you know, those that look, tau and T. And if you're not 100% sure which is which, it's easy to get those mixed up. So try to remember the equations as the names or the concepts. And yeah, the symbols will go along with it, but the symbols could change. Last kind of stress. Bearing stress is the last one we're going to talk about. I don't like the figure in the book. So here's my figure. We're now going to take this axial member and we're going to push on it top and bottom. And that's, we're going to push on there with a force F. And that's going to create a different kind of stress. The first type of stress we did was tension, where we pulled it. And this is, we're now in compression. And so this is a compressive, this bearing stress is a compressive stress. And it's got the equation sigma is equal to force divided by area. Exactly the same as the tensile stress. Difference is, if you want to look at one, our forces here, the forces that we use are now going to have the opposite sign. That's the difference. That force for a compressive stress is now going to be a negative in general. That's the way we will define things moving forward, is that a compressive, this force on the object, will be a negative. All right? Before we start jumping into homework problems, before we start pursuing that, we should look at the units. So the two equations that we've got are average normal stress is equal to force over area. So what are the units of sigma? Well, that's equal to a force. Now, what's a force? Well, we can do that either in pounds or we can do that in newtons. And if we have an area, that's either going to be in inches squared or it's going to be in meters squared. Now, we could use millimeters, we could use feet, but in general, we're going to get pounds and inches squared or newtons and meters squared. Now, both of those have a derived unit or a different way of expressing it. We do it so often that pounds per square inch is just PSI. PSI. And we may, if we get, these numbers do get really big, so we may go to KSI. But that's going to give us our English units. In the metric, we're going to go to pascals. And if you've been paying attention in your thermal class, you know that we talk about kilopascals because pressures are very large. We get 101 kilopascals, right? Or 100, oh, see, now I forgot my units. Not only are we going to get kilopascals, we're going to get megapascals too. We can get any one of those as our units. Now, that's for normal stress. What about for shear stress? Well, if you recall, this force V, it's a force. That's the force in shearing, not our normal force. It's a force in shear, but this is still a force and an area. So our units are the same. They're either going to be in PSI or KSI or pascals, kilopascals, megapascals. All right? There you go. Now we're ready to start doing some homework. So the next presentation is going to be example problem 2.2. All right, see ya.